size matters for piping. So, well-dimensioned hydraulics, how to calculate the right pipe diameter. Then we're also going to have a section about overflow pools, how to choose the right balance tank, and so on. And last but not least, one of your favorite topics, you're talking about the eco mode.
Eco mode for overflow.
For overflow
to show
pools.
how you can save a lot of energy and with this money for your customers.
Yes.
Don't give this money to your customers. We will invest it in bigger filters, of course, in AFM and in flowies and in best pool technology to bring them to the next level.
Exactly.
Good.
And then, as always, at the end, you will have an opportunity to ask your questions. And you have two ways to do this. You can type in your questions here for Q&A, and we will answer them at the end of our session. Or you can type them in here in chat for suggestions and ideas. Okay. Another thing I want to mention here before we start, every session is recorded. You have an opportunity to watch the replay online. Here on our website, they will be posted for 7 days and then be replaced with the next one. And over here, you have an opportunity to download the program of all 10 sessions, plus a printout, a PDF printout of the slides that we are presenting today.
That looks like this. This is for notes that you might want to take.
Everything is on drydenaqua.com.
Yeah. And the speed is high, as always.
Absolutely is high. So, summary session number 1 in 3 simple steps.
Okay. Step number 1 reminds me on an American friend of me, George Gammon, right? Yep. Turnover times in private pools for every 4 to 6 hours and minimum 3 to 4 full cycles per day. Please best use variable speed pumps, you know, that you can slow down during nighttime, save some energy, get better filtration, less good hydraulics. That's step number 1.
Yep. Step number 2, make sure that you have an equal flow distribution. Remember the Staghorn distribution that we talked about in the first session. This is to avoid dead zones. Step number 3.
Step number 3 is believing is good, knowing and controlling is a lot better. That's at least what my wife says. She tries to control me all the time, and that's for control the flow. And the best you can do this is flowies.
Exactly. Okay. Summary.
Session 1 done.
Done. Summary of session 2 in 3 simple steps. Step number 1.
The lower the filtration velocity, the better is the filtration performance.
We
would suggest 12 gallons per minute daytime, 9 to 8 gallons per minute nighttime.
Yes. Step number 2, remember software and hardware. You need good software and good hardware to have a great system. Our AFM is the best software you can get.
The very best.
The very best you can get. So make sure you also use the best hardware that you can get. But what happens if that's not the case?
It will still work very well. It will be still working a lot better than with sand. But of course, the software can operate easily. Go for proper hardware.
Exactly.
And step number 3.
Step number 3 goes back to me. What gets into the filter needs to get out. So you need to have proper backwash velocity, which means make sure you have a minimum of a 15% bed expansion to be able to evacuate the dirt that you're collecting.
Yep.
Yep. So
and that for we need 16 gallons per minute.
Exactly.
Okay, next slide.
So this session now concludes our sessions on hydraulics. We mentioned this pyramid before. With the pyramid, it shows that hydraulics is really the foundation on which everything stands. You need to make sure that you get the foundation right, because otherwise your building is going to look like this, and the pyramid's going to be upside down, and it will be very difficult or impossible to fix it. So get your pyramid right. Okay.
And that for this session is really important. Okay.
Let's jump in.
Yeah. Yeah. And the next one. So first about piping.
Yes.
You want to take this? Because
Sean?
That's okay. Sean?
Sure. Yeah, just looking at definitions of pipe diameter calculations. This can be confusing if you're not familiar with it. NPS is nominal pipe size. That's essentially the center line of the pipe itself. The OD is the outer dimension. The wall thickness, Schedule 40, Schedule 81, and 120 determine based on the outside diameter what the inside diameter is going to be. So a Schedule 40 pipe, 1.5 inch Schedule 40 pipe will actually have a larger inside diameter, or ID, than a 1.5 inch Schedule 120 pipe. For our purposes, the inside diameter is really the most important thing when we're calculating flow velocities and pressures.
But in America, usually you're talking in inches. Is this correct?
That's correct, yes.
Okay, good. So let's talk in inches.
Yes, absolutely. We make it easy for you too,
good.
right?
Yeah, I see that for the first time.
So here's the calculation, Sean.
Yep. So again, if we're looking at a 1.5 inch Schedule 40 pipe, the outside diameter of this pipe is 1.9 inches. The inside diameter is 1.592 inches. We can do a calculation to figure out what the area is on the inside so that we can calculate a velocity, or we can use a simple chart and we know that 1.99 square inches is the inner area of a 1.5 inch pipe. Using the formula that we show below, we can determine what our velocity is, or what our flow rate is that we can achieve in these pipes. So for a 1.5 inch pipe, if we're looking at a 5 foot per second flow velocity, using the formula below, we determine that is a 31 gallon per minute flow rate. So a 31 gallon per minute flow rate in a 1.5 inch Schedule 40 pipe gives us a 5 FPS flow velocity. What's pretty incredible is that a 2 inch pipe, not a whole lot bigger and not a whole lot more expensive, is going to give us 65% more flow at the same velocity. And that's because the inside diameter is much larger, or excuse me, the inside area is much larger at 3.29 square inches. So again, at 5 foot per second flow velocity, we are able to achieve a 51 gallon per minute flow rate.
Okay. The consequences of this.
Right. So what happens if the diameter is too small? Yep. Go ahead.
No, you go ahead.
Okay. So again, if we use pipes that are too small, 1.5 versus 2 inches in this example, our pressure loss is going to be too high. We're going to have a very hard time achieving proper backwash speed, and our energy consumption is going to be considerably higher. If we're looking at this 2 cent per kilowatt hour times 24 hours, that's 4 kilowatts. It's $1 a day. So we can easily achieve an ROI, or a payback, with using a larger pipe within a year. And we'll do some examples of that in a few slides.
Payback in not in months, maybe even in weeks.
In weeks, yes.
It's a no-brainer. Forget about 1.5 inch, go for 2 inch. This is not money.
And I didn't believe Dominic. So we have a calculation later on that shows you that he's actually right. So
you're like my wife.
Anyway, good. Okay, so pipe size, 3 factors. One thing that a lot of people think, right? They look at the connection of their pump, and if it's a 1.5 inch connection, they believe the pipes also need to be 1.5 inch.
Yeah, that's exactly. Maybe it's not the best picture that you choose here for pump, because this is 2 inch on both sides. But for instance, a normal spec pumps very often 2 inch on the suction side, 1.5 inch on the pressure side. And then, at least here in Europe, many people say to me, "Oh, well, Dominic, I stay with 1.5 inch because that's the smallest part." But this is wrong.
Yes. So what's right is 3 factors that have an impact. One is length. The longer your pipe, the higher is your pressure drop, right? So that's number 1. Number 2 is velocity, and velocity is the most important one of the 3.
It's the key factor.
It's the key factor. So if you double your velocity, the pressure drop in your system will increase by a factor of 4. The impact is huge.
And this is, okay, go on.
This is why we recommend pipe velocities on the suction side to not exceed 5 feet per second. On the pressure side, we can go a little bit higher. We are between 5 to 6.5 feet per second. We'll talk about this later on.
These are really the numbers you have to keep for today. This is This is really the message.
Yes.
Please accept this, and you always can go lower, right? That means bigger in the pipe dimension, but not smaller.
Exactly.
What do you have here about turbulence?
So turbulence really talks about the fittings, right?
Yeah.
So different fittings give different turbulences.
Yeah, because, in a straight pipe, you have some friction, and with this pressure drop, but if you come in a fitting, 90 degree and T, etc., you get a high turbulence. And so the more turbulence you get, the higher is your pressure drop. And that is always goes together with the speed. So the speed is important for the length, and it's important for the turbulence. And we want to explain you this in detail, but relax, finally you only have to control the speed, and then you manage everything. So it will look difficult or complicated, and finally you will see it's so easy.
You will see the light that it is actually very easy.
So stay on.
And we have something here for you that is going to make it very easy.
We already won.
Okay, so let's take a deep dive here. First, let's talk about velocity and length. So we're talking about friction loss in pipes and what that means. These are two busy graphs that you see here. Let me explain them to you. Over here on the right side, what you see on the horizontal axis is flow in gallons per minute. And then here on the vertical, we have the flow velocities in feet per second. So plus you have the colored lines here, which is the pipe diameter. So for example, if we have 50 gallon per minute flow, and we use a 1.5 inch pipe, your velocity through the pipe will be 9 feet per second.
Which is too high.
Which in that case would be way too high, and we explain you why. On the left side here, we have a graph that also has the flow in gallon per meter, and then on the vertical, it shows friction loss in PSI per 100 feet. And we have the colors here, which is the indication of the pipe size. So again, we have 50 gallon per minute, and we use an 1.5 inch pipe. That means we will have a friction loss or a pressure loss of 7 PSI per 100 feet of pipe.
That's why it's red.
That's why it's red, right? So we take an example here. We have, again, 50 gallon per minute flow. We have a pipe size of 1.5 inches. We have just calculated here our flow velocity of 9 feet per second, and that will give us a pressure loss of 7 PSI per 100 feet. Now, if we go a size up, if we go to a 2-inch pipe, then we go over here to the right. We have still the same flow, 50 gallon per minute. We go up to our 2-inch pipe, which is yellow, which gives us 6 feet per second flow. This is the maximum that we recommend on the pressure side, okay, 6 feet. That's an equivalent of about 2 meters.
Yeah, huh? I got it.
And we look at the friction loss here that we have. So at 50 gallon per minute, we go up to the yellow line here, which is this here. We go over, gives us a pressure loss of 2 PSI per 100 feet.
Which is pipe, much less than 7.
Which is three times less.
You're good in
calculating. 3 times less. Huh?
This is why it's
significant. Significant. That's why it's green, right? Yeah. So this is the calculation over here. And then we could go even a size up, 2.5 inches. Same calculation here. This will result in a pressure drop of 0.8 PSI and a velocity through the pipe of 4 feet per second, right? So what you can see here is by something that Sean just mentioned, by simply going up from 1.5 inches to 2 inch, you are lowering your pressure loss by a factor of 3.
Yeah.
And you have a pipe velocity of 6 feet rather than 9.
Yeah, and this for an additional price of, I don't know what's in America, my guess is probably $1 a meter.
We'll calculate
for nothing.
Yeah. Yeah.
Okay.
Yeah. Absolutely.
Okay, we do it later.
Okay, so this was about pipe, pipe length and friction. Now the second part is about fittings.
Fittings, right? Turbulence. And I think already this picture here explains a lot. You see the group up there, they have a lot of water, short line, and especially they have no friction, right? and the guy below, he has a lot of friction, a lot of fittings, and a small flow.
Yes. So the table over here on the left helps you understand this. If we have a flow velocity of 2 feet per second, for example, we will have a friction loss of 0.027 psi. Now, this is at a coefficient of 1. I don't want to complicate things, but just keep this in mind. This is a Greek. I think
Lambda,
it's a Greek.
yeah.
It's
not
called lambda.
Lola. Lola is something else.
Lola
That's
is
lambda.
This is lambda, right?
That comes from Greece, yes.
Or, if you have 4 feet of velocity, then you can see that your pressure drop actually quadruples, right? Goes from, so keep this in mind. When you increase your speed, your friction will go down by a factor of 4.
If you double your speed, you increase by a factor of 4.
Exactly.
Huh?
Yeah. Thank you.
Easy to keep.
So this is let's put this. Why is this not moving? It's not moving. There it is. There it is.
Good. Well done.
So now let's bring it together here with the fittings, right? We have.
Let me do also something.
Okay.
I'm not just here for good looking. I'm not. Okay, we have seen this here, this lambda 1. But if you have a 90-degree angle, this is not 1, it's only 0.8. Or if you would go in an elbow, because it's less friction, it's only a lambda of 0.5. Just the opposite, if you have a T, where you got in and you split it, you have a lambda of 1.5. Or angle 45 degree, it's 0.3. So if you need 2 of them, you have 0.6, where here you have 0.8. Now, how do we do this? You will explain us, because it's feet and not so comfortable.
Yes, no problem. So, okay, so let's take this example with 3 feet per second here, huh? So at 3 feet per second, we have a lambda or a pressure loss. I can't quite see it. I see Sean over it.
0.061.
Okay, great. So
I'm his assistant.
Thank you. So we take that, multiply it with lambda, which is 0.8, and that gives us a friction loss for that particular fitting at 3 feet velocity of 0.43 psi, right? If we take the elbow, an elbow has a different coefficient. So we multiply this by 0.5, and then we have 0.03.
Because at the lambda 1, it's 0.06,
Yes.
and you see the T is 0.091. So with this, we can compensate, that there are different fittings with different frictions. But where it's always the same, if you double the speed, see the example between 2 feet and 4 feet, it will double in pressure loss. And with this, in energy consumption.
So,
is that clear in America, Sean?
Oh yeah.
You think?
Yeah,
as we
I think
said,
so.
we're gonna make it. We're making it complicated so we can make it simple at the end.
Yeah,
you
but
will
still
understand.
good. Once to understand it, then you understand lengths and try to avoid fittings. If it's not nice, if it's needed, it's needed. Okay.
Yeah, but especially try to avoid those fittings with a very high coefficient.
Yeah, but if it's needed, it's needed. Just go down with the speed by making the fitting bigger, and you compensate.
And you
for
will
it.
be fine. Exactly. Okay, so now we're bringing it together. Let me just bring this
That
in
looks
here.
horrible.
This looks really good. Okay, so you have seen these 2 graphs before. They will help us identify friction loss here and velocity through the pipe. We make an example. We have a flow rate of 50 gallons per minute. We have a relatively short piping of 100 feet, and we are using 10 90-degree angles. So if we have an 1.5 inch pipe, then we can go again back to this schedule. It will tell us that we have 9 feet per second velocity, which you see here. And then for the resistance here or the friction loss in the pipe work, we choose this graph here. We have 7 psi. That's always on 100 feet, calculated on 100 feet. So 7 psi. This is the pipe. Now we add the fittings, and the fittings are calculated using, again, this graph over here. We have speed of 9, which gives us this resistance here.
0.5.
Yes, times 0.8, which is the coefficient, times 10, because we're using 10 of these angles, gives us 4.4. Total resistance, 11.4 psi.
He's really good at math.
Yes.
Yeah, I'm impressed.
I got it.
Okay,
I
good.
got it.
So
we move on.
Give us the 2-inch
to
story.
the 2-inch. Same story for the 2-inch. We pull the information from here. So we have 2 psi and we have 6 feet per second, which is this. We can calculate the total length that we have here. So we're losing 2 psi from the pipe resistance, from the fittings. Same here. We have now a different length. So we take this resistance times the same coefficient times 10, 2 psi, total 4.
You said it wrong. We have a different speed.
Different speed,
yes,
6. Yes,
yes. Just to make it sure.
Versus
just to tell you,
9.
I was listening to you.
Yeah. Good,
so,
good.
Speed
I like
6
that.
and 0.24
yes.
Multiplied with lambda 0.8, and that gives you the 2 psi.
Now you can do the same calculation, of course, with 2.5.
Yeah, this we leave to you.
Inches. We're not doing this, but what can you see from it? I mean, what's the key takeaway from this?
Yeah.
If you go from 1.5 inches to a 2-inch pipe, you're reducing your friction loss by more than 50%, almost a factor 3 again here.
Yeah.
Significant, significant.
And this for very few money.
Yes. So this is for residential pools, smaller pools. Then we also have a couple of short slides on large pools. Sean, anything to add here?
Sure. If we look at larger piping, it's
Sean,
the same.
Now we can hear you.
Okay. Yeah. So if we're looking at larger pools with large piping, like a 4-inch pipe, for example, and a flow rate of 500 gallons per minute, it gives us a velocity of 12 feet per second, way too high. And working through the similar calculations, 100 feet of piping, 4-inch pipe, 1090-degree angles, with a speed of 12 feet per second, we're going to have a 7 psi loss in just 100 feet of pipe. And with the 10 angles, we have a 7.8 psi loss, giving us a total of 14.8 psi in pressure loss. And if alternatively, if we are to go up to
that's a no-go, huh?
Yeah, this is not a good situation.
Yeah.
If we go up to a 6-inch pipe, same flow rate, our speed, our velocity drops down to 5 feet per second. And again, working through the same calculations, we end up with a total pressure loss of only 2.05 psi. It's a significant difference, and this is going to allow the system to operate correctly, make sure that we can backwash correctly. And again, this is why this is the foundation of the pyramid. If we mess this up, no amount of chemicals is going to be able to correct this.
Yeah, and Sean, let me add something. I just quickly made the math. That might say if you work with the 4-inch, probably you will have to use 7.5 kilowatt pump, to overcome this resistance. And here with the 6-inch pipe, are we 6-inch?
6-inch.
6-inch pipe. You can do it with 5.5 kilowatt. So that's 2 kilowatt of difference every hour, 24 hours, 365 days. So it's massive. It's really massive.
Absolutely.
Public pools, it makes a huge difference to make the right pipe sizing. But of course, it's good that we can backwash properly, but also economically, it's a no-brainer.
Absolutely.
And American friends, it's a no-brainer. Yeah,
it is.
I'm getting emotional in this subject. Sorry for that.
Yeah, that's okay.
You invited me.
Yeah, it's good. That's what we like about you, your emotions, right? So the method we just showed you is a little bit of Stone Age, huh? But why did we do this? Because it really helps you understand how this works, right? Yeah. When you understand the detail, then you understand the bigger picture. Of course, there are apps. There are programs available that help you calculate this. For example, this tool here that you can download there's several. This is a pretty good one. But really, what we also have is we have a tool. It's really the old-fashioned way. And I have to say this is currently metric. So based on your feedback that we hope to get from today's session, I would like to hear from you whether this is something you would like from us in Imperial, so you can use it. Let us quickly explain how this works.
Yes. Short, yeah, as he said, we are happy to do this, you know, if you get a lot of orders for AFM or for calculators, but please then really use it. I wear it all the time. I even sleep with it. It's so useful. And of course, apps is great, but you're in a technical room and you quickly want to calculate. You don't have internet connection. This always works. Always.
Yes.
Okay, explain it.
So
I show it.
He invented it. I have to explain it.
Yes.
Life is not fair, right?
No, I didn't invent it. I just copied it from GF, by the way.
Yeah. Okay. There's nothing wrong about that, right?
Yeah. Copy the good things.
Copy and make it better, right? So pipe diameter. So the phase here will basically take you through this step by step. It's a 3-step approach. It couldn't be any easier.
Really see
you know,
just
no.
Show it on
and we show it here. So the first thing you're going to do is, well, it's going to show you flow rate. It's going to show you the inner pipe diameter, and it will show you the pipe velocity that you will get. So first step is to choose the flow rate that you have in your system. This example, we're using 15 meter cubes per hour. So you can move this in here to adjust to that velocity or to that volume, water volume you're moving.
But we will do it in gallon per minute.
We promise,
version,
right?
Yeah.
Then you will decide or choose the velocity, the maximum velocity or the range of velocity that you want to see. What we mentioned before is we, on the suction side, we are between 1 to 1.5 meters, which is an equivalent to about 3 to 5. And then on the pressure side, from 5 to 6.5. And you will be able to read this from here. And then based on that, you can identify the pipe diameter that is necessary to achieve that.
So here it would be for us 2.5 inch.
2.5
on the suction
inch.
side, it would be 2 inch on the pressure side. So very easy. You will see it. So this is, I love this. I really, really love this. And we give this also here in Europe and in the rest of the world as a present because it's a typical Triton present. It has a lot of value and doesn't cost a lot.
Yes.
And this is what we like.
Absolutely.
We have a Swiss, Scottish DNA, and the Scottish, Dagobert Duck. I mean, we are not as rich as he is, but we don't like to spend money.
No.
We do it if we have such a good instrument.
Yeah.
Philip, I have one question.
Yep.
Why is suction lower in the speed than pressure?
I think you told me this before, but
I do it in the American version. My version was maybe not that American. No, but in general, it's a lot easier to aspire than to what is the other thing? To aspire, and the other is in English?
To push.
To push. The maximum vacuum that you can produce is 1 bar. You can't do more, and you will never achieve it.
Mm-hmm.
On the pressure side, you can go 1 to 100 psi or whatever, but the maximum vacuum is 1 bar, which is 10 psi, around
14.
Also you see this in the pump. We can aspire or suck maybe 5 feet.
Mm-hmm.
Yeah, 3 meters.
Yeah,
but you can pump 100 meters, so that's
3 meters or 10 feet.
So
roughly,
it's a lot easier to suck than to push. Yeah.
Okay, we leave it at that.
Yeah.
Huh?
Exactly.
Okay. Summary here of pipe sizes. If we have a gravity, a return line from a balance tank, from the overflow to the balance tank, we recommend you go at 1.6 feet per second.
Then you're safe.
Or then you're on the safe side.
It's gravity. It's gravity.
It's gravity, right? If we are looking at the suction side, so everything before the pump, right? Then we recommend you go with 3.3 to 5 feet per second.
Yeah, let's make 3 to 5.
Yeah. We can round
the lower
a little
the
bit.
better.
The lower the better.
3 or 5?
It's 3 to 5, right?
Yes.
So if you have very long pipes, a lot of resistance, you go with the lower flow because you have less friction.
Yeah. It's all about friction.
If you have shorter lines, then you can go with the 5.
Yeah.
We're changing. This is the picture for manifolds. If we have manifolds, collector manifolds, then you can also go with a slightly lower velocity, 1.6 to 3.3 roughly.
Yeah, or to get an equal distribution instead of stack on. Before we had stack on, this would be collector, that you get an equal distribution to the pumps.
Exactly.
Yep.
And then we change to the pressure side here. Like we mentioned, anything pressure side is anything after the pump. We recommend between 5 to 6.5 feet per second. This is true between the pump and the filter and the filter and the pool. Okay. Conclusions on pressure loss. You know, the main takeaway from this piece is really, if you double your speed, then your pressure loss will quadruple, or vice versa. If you have your speed, then your pressure loss will go down by a factor of 4. If you lower it by a factor of 4, that means you lower your energy consumption by a factor of 4 as
Absolutely.
well, right?
If there would be no resistance, you know, no friction, no pressure drop, you know, you would not need any energy.
Yes. So pipe speed is the key here. Okay.
Oops, again.
So this is our calculation example, right, Sean, that we calculated through.
Right.
Worse and worse.
To show cost savings, because I didn't believe you, right? So what do we have here? Same example we just did.
Yeah. So this is exactly what we looked at before. The difference between a 1.5 inch and a 2-inch Schedule 40 pipe, a difference of 7.4 psi pressure loss. So
yes. So what does that mean now if we put some dollar numbers behind it for us, Sean?
Sure. So looking on return on investment, your payback for going with the larger pipe diameter, well within 1 year. It's well within 1 year. So looking at the cost of the piping itself, it's about $2.30 more per 10 feet to go with a 2-inch pipe. It's nominal. It's negligible expense. $23 is all in 100 feet of pipe. The fittings, the 90-degree fittings, say about the same thing, about $2 a fitting at most. So your total investment to go with a 2-inch pipe over a 1.5 inch is only $43. It's a no-brainer, as we've said. It's nothing. But the big benefit here comes with the fact that because we're not trying to pull or push so hard through this tiny 1.5 inch pipe, we're able to use a smaller pump. This is a pump curve that we have on the left. And if we use the head pressure differences between the two pumps, we can see that we can actually use a smaller pump that consumes considerably less energy. So of course we want to consume less energy anyway for sustainability reasons, but also it's a nice thing to have an extra $115 a year in your pocketbook, because, and this is only for 150 days. This is a pool season. There's pools that run 24/7, 365 days a year. Their savings is going to be even more than that. So $115 a year in savings. Obviously, we make up the $43 additional expense pretty quickly.
Philip and John, I have a question. How is this if you have a variable speed pump controlled by a flowies?
Sure.
Okay. I save you guys exactly the same. You know, maybe you have in the 1.5 inch, you have to run it at 2,500 RPM. If you go for the 2-inch, you have to run it at 2,100 RPM. So it's exactly this. And it's dollars, okay, but even more important for me, it's energy. 800, more than 800 kilowatt hours. That's a lot of energy. And we stand for green technology and clean environment. So please do it. And now, ladies and gentlemen, I understand the word no-brainer. That tells me everybody who works with 1.5 inch has no brain. I understand it really. That just came in.
It's a learning curve, right?
Yeah, sure.
And it's a learning curve. This is part of what we do here.
No, I know I do this a little bit, emotional and aggressive, really to convince you, convince you.
This, by the way, is his 4th session today. After doing it in English, Spanish, French and German. Now he's helping out today. So, and it's almost cocktail hour here in Switzerland, right? So
let's go on.
We move on.
I'm getting thirsty.
Yes. So backwash pipe velocity, you know, we mentioned no higher than 6.5 feet per second. This is important to have a proper backwash. This also means never go up with your backwash lines. Always go down. You have an example here from Italy.
Yeah, because
right?
you make a bottleneck. You make a bottleneck. You know, even in Germany, it should be pressure-free. Here in Italy, you see perfectly done, you know, even with this side glass, but it's the wrong direction. It goes up. It does not go down. So really, backwash water always should go down. That you have this, Nadine, let's play it. And you see, especially I choose here, that's also in Italy, you know, we want to see in the side glass that expansion, we want to see the backwash. And this only really works if you go down. Shall I take this one? Yeah, that's one of my favorite. You know, here, this is what you see around the world. You know, here you see a beautiful filter from Astral, great manufacturer. Filter diameter is 2000 millimeter. That's 80 inch. Filter surface 35 square feet. Backwash velocity 20 gallons per minute. Backwash flow, I guess that's 700. Yeah.
Yep.
Okay. You can buy this filter, and this is something I do not understand from this manufacturer, and I do not understand, you know, this from anybody who builds this in. You can buy this filter, you know, with 80 inches. You can buy it with 4-inch connections or with 6-inch connections. And here they say this is for 20 meters per hour. That's
8 gallons per minute per square foot.
Exactly. And this one is for, Philip?
20 gallons per minute per square foot.
Otherwise, it's exactly the same filter. It's exactly the same filter. It's just the connections and the inner piping is 6-inch, and here it is 4-inch. Now, I agree, you know, if you would never backwash this filter and you use it with sand or with AFM, whatever, then you can work with this, right? But remember, filtration is a bin. You fill it and then you have to backwash it. And to backwash it, you need a bed expansion. We talked about this in session number 2. And for this, you need a certain velocity. And this is this. And you really need this. So this, the red, and also this and this has to, it should not be forbidden. It shouldn't be forbidden. Don't use it. This is wrong. You know, everybody who does this show his incompetence. It's not going to work. It's working in filtration, but it's not working in backwashing.
Yeah.
Was it emotional enough?
Yes.
Anything to add?
4th time? No.
Okay.
So dimension your filter based on the backwash, not on the filtration
and
velocity.
Please, all the filter manufacturer, if it's Hayward or Astral or whoever, sorry, shit. Please. Oh, that's the wrong side.
Yeah.
You make me nervous. Only green. We want to see only green filters.
Yep.
Always in this. And you can double check this again with our magic ruler. Look, in Germany, Dean would use the same 80-inch filter with 10-inch, I'm getting nervous, with 10-inch here raw water and 8-inch clean water, you know, with a velocity of 3 feet per second.
Yeah. It's perfect.
That's perfect. But you don't have to do it that good, but allow please not more than 6 feet per second, I guess.
Exactly right.
Huh?
Not more than 6.
Yeah.
Okay, so you came back recently from a pool in Belgium too,
if you talk 4 years ago, as
yes.
Yes. No, they asked me, we want to use here AFM.
Oops.
We have too high of combined chlorine. And because it was a new partner, I was in the area, I went there. Go to the next one. They had nice filters, 64 inches, but only 4-inch piping. They had 2 beautiful pumps, you know, Hairborn, which is the very best, you know, that you find, I guess, in the world, or at least in Europe. Both of them 5.5 kilowatt. And their assumption was both of them are bringing 220 gallons per minute, totally 450 gallons per minute, also to backwash the filter. Backwash we would need 450 gallons per minute, right? Problem is, first on the left, the strainer. On the strainer there. This was such a small strainer, you know, 4 liters.
That's 1 gallon.
1 gallon. Okay, yeah, it did not work. You know, it did not work because if you work it with 2 pumps, you always are in cavitation. You try to get more water than it goes through, so you're in cavitation, you get air in your filter, so really not acceptable. By the way, Sean, I didn't know if I told you already, our partner Colplus makes really nice big strainers. Just to mention it. And then finally, you have also the piping with 4 inches. And look at the piping, you know, on the pumps. These guys try to break the world record in using 90 degrees. 1, 2, 3, 4, 5, 6, and yeah, hundreds. And yeah, it really did not work. Go on the next slide. You know, this is what you see here, you know, on the result. You know, if they run the system with 1 pump, they get to 200 gallons per minute. If they added the second pump, remember, with 5.5 kilowatt, they got to 240 gallons per minute. This is great. Now with an extra 5.5 kilowatt, you achieve 20 gallons per minute. This is terrible. And it's really just because the strainer much too small. That was the main problem. The velocity much too high and too many fittings. Maybe you just can explain on the 1T.
Yeah, so we're using the 1T here with 4-inch T, which gives us a pressure loss of 1.7 psi, just that 1T.
Remember,
at that high velocity
lambda
that we have,
1.5.
right?
It's the highest lambda that we have.
Exactly. So if we just change that T to a 6-inch, the pressure would drop by half.
And we talk about 1T.
Yeah.
Okay, and it was measured. Yeah, not with Flowys, but with this, that works as well.
So you walked away from this, right? There was nothing we could do.
No, I told it, this was especially, this was 4 years ago when we didn't have the new FM, AFN, and G, where probably I could have done it in a way, you know, very, very much compromise, but as I said, with the old one, no chance. You change the strainer, you change the piping, we will not touch it. Today we could manage it, but not really good.
So here's another beautiful example that we brought home from China. You see a 48-inch Chinese filter here. Pipe connection is DN50, 2-inch. Backwash velocity, 18 gallon per square foot. That's what we require. Gives a flow rate of 230 gallon per minute. This gives a pipe velocity of 22 feet per second.
World record?
We said 6.5 is the maximum. You should not go higher than that. So world record. So this is too small. You will never be able to backwash this filter.
Yeah, especially with the multi-port valve. You know, in a multi-port valve, this is the loudest fitting that you can have because the water has to change 6-7 times the direction. And maybe you show it quickly here on you know, if you have 240 gallons per minute, you know, and you have a 2-inch multi-port valve, you can use a 100 kilowatt pump. You cannot backwash it. It's not possible. There is physical limitations.
That's physics, physics, absolutely.
So we call this the China virus. Oh no, the Chinese filter.
Yeah, exactly.
We don't want that.
Exactly.
Yeah, that's another nice one.
So I think I was in the bar. You went to the pool, right?
Yeah,
is that,
this is how we play together, right? It was a nice pool. And they had 200, maybe you lead
yeah,
through,
okay, so we had 4 pumps at 5.5 kilowatt each, with a, you know, estimated volume 900 gallon per minute.
That's what they said.
That's what they said, right? So the filters, they looked pretty good too, right? 48-inch filters, an 8-inch collector. So that
3-inch multi-port valve, that was okay.
That was okay, right? Yeah. But then the problem started, right? Going from the 8-inch to 2 times 3.5-inch pipes.
Yeah. And if we have this in American version, you will see you get at the speed of, oh shit, what is it, 6 meters?
Times 3. So 18.
18. And and then all of this flow goes then in 4 lines, return lines of 2-inch. You know, and I really didn't want to be rude. Maybe I was. I told them, listen, guys, you will never have 900 gallons per minute. You will not have 400. And but it is. And look at the pumps, and it's great. And I said no. And then by chance, I've seen the blue-white flow meter, which was installed on the main pipe, on this 200 millimeter pipe. And I looked at it, and here it's in our version, it's 800 liters per minute, which is 210 gallons per minute.
That's 25%, huh?
Yeah. So let this suck in. You invest 22 kilowatt hours of energy to get 210 gallons per minute. If you make the proper sizing, you can do this with a tenth, or at least with 20% of this energy. So this is a shame. It's not to blame them. You know, they got it now. It was existing, was not there. But these are the things that we want to fight against, because this is completely wrong. This is not good for the planet. It's not good for our industry.
Mm-hmm. Yeah. Okay, we're changing over to overflow pools,
yeah,
and balance tanks. So we brought an example here also from China. This is the Beijing Hilton, a beautiful pool, an older installation.
Very old. Probably just after the Cultural Revolution.
Yeah,
they built
probably.
It.
Our partner had an AFM filter installed a few months before we arrived.
No, he just replaced the media. The filter was installed.
Yeah.
It was a terrible installation, to be honest.
So there were two complaints. One was, there's foam forming on top of the surface. There's some oily residues, from the bathers. The second complaint was that they couldn't regulate their pH and chlorine. It was constantly overshooting and
undershooting. They had an automatic dosing station, but it was always overdosing and underdosing, overdosing and underdosing.
Yeah.
And, first they said, well, why do we have this foam on the surface? Because we have AFM. And actually, you see this here from the picture. The water clarity was good. Honestly, I couldn't believe how good it was, for the lousy filtration they had. It's quite a big pool, and they had 24-inch or 30-inch filters. Yeah. Terrible pipework.
So what did we see? We saw that, the pool had 4 inlets on one side and a distance of probably 20 meters, 20 yards to the drains, right? To the bottom drains. So it would take the water about 8 hours to travel. So the chemical dosing, whatever they did, would not get back to the reader within
you start dosing chlorine or acid, and it goes 8 or 10 hours until you get the result. And this is why you have overshooting and undershooting. Very clear. But the other ones, look at the overflow here. Dry.
Oops, sorry. Yeah.
Dry.
Dry.
Yeah. Honestly, we didn't find it. It took us a moment to find it out, but then we did, because we were then in the technical room, and Philip said, where is the balance tank? And the answer was, there is no balance tank. So, the splash water goes directly to the drain, because they said, well, we don't have a space for a balance tank.
Yeah.
But that makes it for the surface water, and the surface water is the most polluted water. The best water is the groundwater. The surface water is the most polluted water. That's really hard for this surface water to get to the filter. It just will never come. It has to stay for hours on the surface and maybe then to sink. So the only way how you can avoid it is really to overflow, balance tank, and then you to your filtration. Then you also would have a much better mixing. The mixing they had was terrible. I mean, the pool hydraulic is just terrible.
Yeah. So if you cannot overflow, then it would have been much better to do a skimmer pool, huh?
Absolutely. Yeah. Because the surface, the first 30 centimeters is the most polluted part, and the floor part is the best part. Yeah, and this is why you should always, if you use the pool, overflow, and you should use it really with 100%, ideally. Very often in Asia and also in Southern Europe, they're overflowing with 10%, and then 90% goes through the main drains, and this is not good. And they just do it, to save money on the piping from the gravity return line. So it's not our solution. If you do it, you do it, but it's not our solution. Okay, talking about balance tank, make one more.
Yep.
Okay. Now, Philip will show you, he's so brilliant. How you can backwash your overflow pool a lot smarter.
Yes. Okay. So a simple 3-way valve here. This could be the Besco valve. There are other products on the market. This could be also a manual 3-way valve.
Whatever.
Can have a lot of advantages and save you a lot of money. Reason number 1, if we pull water from the bottom of a pool to backwash a filter, we're getting the cleanest water in the system to backwash the pool. the water that's pulling from the balance tank is actually the dirtiest that we have in the system. So a very good reason is to pull your backwash water from the bottom drain, because it's the cleanest that you can get.
Wash your filter with the best water.
Yes.
Not so important, by the way, for AFM, but really important for sand.
Yes. Reason number 2, in this case, if you have a geostatic height, in this case, you know, it will help you. It will reduce the pressure.
It will not reduce
it
the pressure.
Will help.
It creates more pumping, because you get an additional 2 or 3 meters.
Exactly.
Or yards or whatever. So it's helping.
It's helping with that.
It increases the power of your pump.
Exactly.
Because here you pump, but you get here an additional geostatic height.
Yep.
But the
and
main
thirdly, and that might be the most important one
for you,
you can reduce the size of your balance tank, because you're not pulling the water from here, you're using it from here.
Yeah, and that's big. You know, especially if the filters are bigger, you know, what we have seen before, that becomes big.
Yeah.
And these are significant savings, you know, in dollars and in room. And again, don't take these dollars and give it to the customer. Take these dollars and invest it in better filtration, variable speed pumps, flowies, and of course AFM.
Yep, exactly. Yep. Okay.
Want to calculate it, or just?
It's just I'm just going to tell you the simple rules here. You can calculate the size of your backwash tank with this formula here, where we have basically 4 factors: the water you need for the backwash, the water that you're losing by displacement from bathers, the displacement that comes from blowers and water attractions, and the water displacement from covers.
Well, you don't have so many covers, I understood,
yes.
in America. So, you know, the numbers we can debate, but that's not the goal. But the important one is the first one, the water that you need to backwash your filter. And you see, it's 50%.
It's 50%. Yeah.
And this means, you know, you can make your balance tank 600 gallons smaller, and this is a significant amount of money.
Yes.
Right.
And in order to save you time and trouble, there's a simple rule you can apply. So what you need to know is the size, the surface of your pool. In this case, a 30 by 15 feet pool. Take 3 gallons of water per meter square of pool surface. So in this case, 450 times 3 equals 1,350 gallons. Apply a safety factor of 1.3. Voila, you have your volume that you need for the backwash tank.
Simple route and exact calculation brings you to the same result.
Yes.
I love that.
Now, the same calculation when using water directly from the pool. So it's the same calculation, but your water loss here is 0. And as a consequence, the simple rule is not 3 gallons, it's 1.5 gallons per square foot. So same calculation here, you're going to need about 850 gallon balance tank volume.
This is great, isn't it? Are you happy with this, Sean?
Yes, absolutely.
Yeah, good.
Very much.
So this alone can save you $1,000 easy.
Probably more.
Yeah, maybe more.
Okay. However, but yeah.
Yep. Okay.
Next
now
one.
Dominic's favorite topic.
Favorite topic. That was a system that we developed in my first career when I was still managing director of Aquasolar, which we developed. What's the idea? In daytime when it's warm, as you can see here, we have here the temperature. Okay, sorry, it's in degrees. We are overflowing. In nighttime, as you can see, when it's cold, we are not overflowing. And maybe you take it because you're better with Fahrenheit and all this. Yeah. But that's the basic idea. I show you it again, how it works. So nice and warm, high temperature. We are overflowing 100%. Normal filtration back to the pool. Now we are getting in the night. Temperature goes down. We are not overflowing. We are in economy mode. Also, we go in speed low. Here in speed normal. Speed number 2. Remember session number 1. And then in the nighttime, we are not overflowing. We reduce the velocity to speed number 1, low velocity. Yeah. That's the idea.
Yeah.
Yeah. And we do this since 15 years. First just in Switzerland, and then it went to Germany and Austria, and now it's all around Europe. And everybody does it, and to be honest, I'm quite happy.
Yes, so again here, what you just said, during the day, we have overflow.
Yep.
Pool is flowing over.
Perfect hydraulic.
Perfect hydraulic. We're moving water. We're skimming the surface. It's ideal. At night, when even when your pool is covered, pull the water from the bottom drain.
Which is a compromised hydraulic, of course, but it doesn't matter. We just want to heat. We don't want to stop filtration because of what we discussed in session number 2, 24 hours filtration. But we avoid that we go over the overflow, because you have the evaporation, and evaporation really makes a difference.
So evaporation has a big impact on energy savings.
Maybe I can quickly explain this. Evaporation you see up there, right? Now you have to understand, you only need 1 kilocalorie to heat of energy, to heat up 1 liter of water. That's 0.3 gallons. Let's keep it in liters, right? 1 liter of water by 1 degree, but you need 540 kilocalories to evaporate the water. I mean, really to change it from a liquid to a gas, and this is more than 500 times more, and that makes really the big difference. And you will see this in the shower. Philip, are you showering?
More than you.
Okay. How do you know?
After a long day, right? Okay. So yeah, you all know this. When you come out from the shower, your skin's wet, you're starting to feel a little bit of cold. And the reason for that,
even when your room is warm,
even then, right? Because the water on your body wants to evaporate, and it does it by pulling energy from your body. That's why your body cools down and you feel cool. As soon as you start drying up, you're fine again because the water's gone.
And that's the same evaporation in pool. And that's true if it's indoor pool or also outdoor pool. It's always the same. This is where you lose your energy. I can give you an example. When I run my pool, quite warm temperature, water temperature, quite fresh in the nighttime. If I run it for 12 hours, one overflowing with a cover, but overflowing, I lose 1.5 degrees. If I do not overflow, still the cover on it, half a degree. So it's quite massive. I haven't seen any of the system where the energy saving was less than 10,000 kilowatt hours per season. And that's equivalent like 1,000 liters of oil. I'm not good in American. Yeah, it's massive.
Massive. It's 250 gallons.
Yeah, maybe you translate this in,
No.
You round it up. You make it
good. Yeah, we use round
American
numbers.
Measurements.
We use round numbers. Okay. Let's.
Last point, that's also for indoor pools. And I can explain you this. If you run it 12 hours in the normal mode, when you swim, for instance, in a jacuzzi or any indoor pool, and then you go in the eco mode during nighttime for 12 hours, then your dehumidifier, he will stop. After a certain period of time, he will stop. It will not run all night long, maybe 10 hours, only 2 hours instead of 12 hours. And this is where you see the energy saving. Okay, let's summarize in 3 simple steps.
Okay, step number 1, when you dimension pipe work, there are 3 factors that are important. Length of the pipe, speed, at the speed the water is traveling, and the turbulence, right? So if you slow down the speed by a factor of 2, the pressure loss will go down by a factor of 4.
Step number 2, use the magic ruler.
Done, right?
Yeah.
Step number 3, make smart energy savings, right? By using, for example, the eco mode.
Let's keep the earth green.
Significant opportunities here. Okay. Outlook session number 4.
In a week, we are back here, same time, same place, and we will talk about biology in filters. We will talk about disinfection byproducts, especially about trichloramines and why they are harmful, how you can avoid it. We will talk about chloroform, which is even more harmful, how you can avoid it. maybe also about chlorates. That's probably not so common in America.
Probably not.
But let's talk about it because it will come. And it will be a very good session. It would be great to have you back.
A very important session, right?
Yep.
So this is beautiful.
Okay.